Hello friends, this is Dr. Varun. For mechanical engineering students, engineering metallurgy is an important subject and easy to score. In that, iron and carbide diagram is very important concept. And many students have difficulty to understand the basic concepts of iron and carbide diagram. And this video is mainly to address this issue, and I hope I will be able to address them for most of the concepts in iron and carbide diagram. So let's start. Hello friends, this is Dr. Varun, and today we are going to discuss about iron carbide phase diagram. Before we start, there are some few terminology which is commonly seen in this iron carbide phase diagram, mostly phase diagram, and what is allotropy. So let's listen to what are they. A phase can be defined as a homogeneous portion of a system that has uniform physical, chemical characteristics. That is, it is physically distinct from other phases, chemically homogeneous and mechanically separable portions of a system. Then phase diagram is a diagrammatic representation of limits of stability of various phases in a chemical system at equilibrium with respect to variables such as composition and temperature. And then allotropy is the possibility of existence of two or more different types of crystal structures at different temperatures. Before we start with iron carbide phase diagram, the pure iron cooling curve is very important. So this cooling curve follows allotropy like we have defined it. It is mainly iron exhibits different crystal structures at different temperatures. So we plot this cooling curve on temperature versus time, and in this we have, like I said, allotropy with different crystal structures at different temperatures. So in order to understand this iron carbide diagram, pure iron is very important. Pure iron cooling curve will look something like this. And in this, very importantly, the temperatures needs to be noted down. So it starts with 1539, 1400, 910, 768 degrees centigrades. So above 1539 degrees centigrade, the pure iron will be in liquid phase. Below 1539 up to 1400 degrees centigrade, the first allotropic change of liquid iron to delta iron in BCC crystal structure for pure iron. This delta iron is in BCC, that is body centered cubic crystal structure, and below 1400 degrees centigrade up to 910 degrees centigrade it exhibits another phase change which is normally called as gamma iron, and it has a phase centered cubic crystal structure which is a non-magnetic. Below 910 degrees centigrade it will again transform into another crystal structure which we call it as a alpha iron, which is again body centered crystal structure, and it's also non-magnetic. And below 768 degrees centigrade the crystal structure will be same BCC alpha iron, but non-magnetic will change into magnetic form, and this temperature is also called as Curie temperature. Now when we observe this cooling curve, we need to understand that the allotropic changes of iron, pure iron, is having basically liquid to delta iron, which is BCC, delta iron to gamma iron, which is FCC, and gamma iron to alpha iron, which is again BCC crystal structure. Now when we going to alloy it from with the alloying elements, we are most likely to get in the same temperatures and same changes from delta to gamma, gamma to alpha. But since it's been alloyed, the pure metal have a constant temperature at which the transformations is taking place, like it is denoted by a horizontal line. Whereas when you alloy them, they may exhibit a temperature range over which the beginning and ending of transformation may occur. So let's start first with how to draw the iron carbide phase diagram. This is very important for the students. Mostly they try to remember the diagram as a diagrammatic representation, but it follows one systematic procedure to draw. So I'll show to the basic sequence of steps you may follow. Firstly, draw the temperature as y-axis and the percentage of carbon, which is the basic iron carbide which we get. So the carbon is being varied from 0 to 6.67 percentage of carbon. So carbon is being alloyed. Now when we do that, mainly iron is accepts the carbon in the interstitial solid solution form. Now I hope you all have remembered about the solid solutions mainly take place in two forms, one in the interstitial solid solution type and other in the substitutional form. Now iron carbide phase diagram, the carbon elements are in the interstitial positions of iron crystal lattice structure. Now when we do that, the carbon, the maximum it can be formed in iron is up to 6.67 percentage of carbon. What exactly happens at this 6.67 percentage of carbon is it forms an interstitial compound. Now mainly you need to understand there are three things. One is pure iron, then alloy, and then compound. If and only if alloy is formed when they obey Humidiferous rules. When they fail to obey the Humidiferous rules, it will end up forming a compound. And we have in iron carbide phase diagram one such compound which is at exactly 6.67 percentage of carbon. So many will have a misconception that what is this iron carbide? Iron carbide is just a percentage of carbon, it's not a phase. And at this 6.67 percentage of carbon, it forms iron carbide, which is represented by Fe3C, or also called as iron carbide, or commonly called as cementite for a common metallurgy aspects. Now the iron can be varied from 0 to 6.67 percentage of carbon. So this is the boundary that which is formed for representing iron carbide phase diagram. Now upon this we are going to start with the same type of cooling curve temperatures that like we have seen for pure iron, except that when the carbon is being alloyed, you'll get a range of temperatures over which the transformations will take place. Unlike in the pure iron, it transforms at a constant temperature. So we have to start with the liquid transformations. So first let us just draw sequentially how the transformations takes place. Now this is the sequence of steps you need to remember in order to draw the iron carbide phase diagram. This is the only step that is to be remembered. Then when we have discussed the pure iron temperatures, more or less the same similar temperatures will also follow in the iron carbide phase diagram. So it's starting with 1539, then we have one intermediate which is 1492, then 1400 again, then another intermediate which is 1147, then 910, and now 723. These are the temperatures which are represented in degrees centigrade. Now like I said, above 1539 degrees centigrade we have liquid, which is this line is our liquidious line above which everything will be in the liquid state. Then below 1539 degrees centigrade at this location, you'll get delta iron. So like we have already discussed, from 1539 to 1400 degrees centigrade, we have delta iron. Now below delta, we have gamma from 1400 up to 910, which is in this case austenite. We'll come back to that. Then below 910, we have alpha iron, which is ferrite. We'll again discuss that ferrite in shortly. Now it is very easy to mark the other phases, the two phase regions. Like in this side we have liquid, here we have delta, so this will become liquid plus delta. Similarly, here delta, here gamma, so in between you'll get delta plus gamma. Likewise, you have gamma plus liquid, and then L plus Fe3, that is liquid plus Fe3C. So it is very easy to point gamma plus alpha here. So on either sides, whatever the phases are present, the two phase regions will have those two combination of phases. Next important thing to do is about the compositions, that is carbon composition. We'll start with the top here, which is having the delta maximum composition is 0.1% of carbon. Then you have here in between, which is 0.18% of carbon, and the maximum here it is 0.5% of carbon. And another one at this particular location, which is 4.3% of carbon, and then here it is 2% of carbon, and here it is 0.8% of carbon, and the maximum alpha it is 0.025% of carbon. At room temperature, alpha is 0.008% of carbon. What we can notice here is delta having maximum percentage of carbon at 0.1% of carbon, gamma at 2% of carbon, and alpha at 0.025% of carbon. When a carbon is dissolved in gamma iron, in short, we call that as austenite. And when carbon is dissolved in alpha iron, we call that as ferrite. We'll also come back to that during the invariant reactions. Now, there are three horizontal lines, one at 1492 degrees centigrade and another one at 1147 degrees centigrade, this line, and the third one at 723 degrees centigrade, and this is line. So mainly these are the lines which are horizontal, meaning they are the invariant reactions. So in iron carbide phase diagram, we have three invariant reactions represented by three horizontal lines, where we get the invariant reactions, and this occurs, the first one, the first invariant reaction, we call that as a peritectic reaction. This peritectic reaction occurs at this point here. So at 0.18% of carbon and 1492 degrees centigrade, the liquid plus delta iron will combine to form a new solid, which is called as gamma iron. That is, liquid plus delta iron gives rise to austenite. This is our first invariant reaction occurring in iron carbide phase diagram. The next one will occur somewhere here at 4.3% of carbon and 1147 degrees centigrade. This is we called as a eutectic reaction. So in eutectic reaction, at 4.3% of carbon and 1147 degrees centigrade, liquid will transform into ends of the line. You can see very clearly this end we have gamma iron, which is austenite, and this end it is Fe3C, which is cementite. So liquid will transform into austenite plus cementite, and this mixture is called as ledaburate. That is, austenite plus cementite mixture is called as ledaburate. The next The last one, the third invariant reaction occurs here at this point, which is at 0.8 percentage of carbon and 723 degrees centigrade, which we call it as a eutectoid reaction. So at 0.8 percentage of carbon and 723 degrees centigrade, we have eutectoid reaction, which is again gamma transforming into ends of the line. This end it is alpha and this end it is Fe3C. So the austenite will transform into ferrite plus cementite, and this mixture, ferrite plus cementite mixture, is called as perlite. So this is what you are supposed to remember. Simply three invariant reactions. One at 0.18% of carbon, which is a peritectic reaction at 1492 degrees centigrade, wherein you'll have liquid plus delta iron transforming into austenite. Then next, at 4.3% of carbon, eutectic reaction, where 1147 degrees centigrade, liquid will transform into austenite plus cementite, and that mixture is called as lead aburate. Then the third one, eutectoid reaction at 0.8% of carbon, 723 degrees centigrade, gamma iron austenite will transform into ferrite plus cementite, which mixture is called as a perlite mixture. Now here another important thing you need to remember here is austenite, which is formed in the eutectic mixture, will not be stable below 723 degrees centigrade. They further transform into either of the forms of perlite. So austenite below 723 degrees centigrade is not stable, which will again transform, that is this transformation line. Next, we are going to understand that in iron and carbide diagram, we have basically two important engineering metals, that is steel and cast iron. So mainly here in iron carbide phase diagram, from 0 to 2% of carbon we get steel, and 2 to 6.69% of carbon we call that as a cast iron. To be precise, it is 0.008 to 2 is steel, and cast iron, it is very brittle, so maximum we may use up to 4.6 to 4.8. We will not even go up to 6.7. So this is steel definition in terms of composition of carbon, that is varying from 0.008 to 2% of carbon is called steel, and 2 to 6.67% of carbon is called as cast iron. Furthermore, you have two important reactions, which is in steel you have eutectoid reaction, whereas in cast iron you have eutectic reaction. So less than the 0.8% of carbon is called hypoeutectoid steel, and greater than 0.8% of carbon is called hypereutectoid steel. Similarly, in cast iron, less than eutectic composition, which is 2 to 4.3% of carbon, is called hypoeutectic cast iron, and 4.3 to 6.67% of carbon is called hypereutectic cast iron. Now, steel portion of iron and carbide phase diagram. When we separate only the steel portion of the iron and carbide diagram, this is somewhat it looks like. And in this, we have only focused on the temperatures from where austenite is transforming, and the carbon ranging from 0 to 2% of carbon. Like we already discussed, this up to 2% of carbon, it is called steel. Now furthermore, we have to understand something about the lines which are represented here, which is the transformation lines, which are also called as critical temperature lines. Now we label them as A3, A1, ACM and A3, 1. They are also called as upper critical temperature lines and low critical temperature lines, but they are on the either sides of the eutectoid temperature line. So in general, they are called as A3 is called as upper critical temperature line on the hypoeutectoid side of the steel, and A1 is low critical temperature line on the hypoeutectoid side of the steel. ACM, similar to that, upper critical temperature line on the hyper-eutectoid side of the steel, and A3, 1 is lower critical temperature line on the hyper-eutectoid side of the steel. Sorry about this. This is hyper-eutectoid side of the steel. Now, if at all we take an alloy composition somewhere at 0.4% of carbon, and we try to understand the microstructure or the cooling of this 0.4% of carbon, something like this. So at austenite we have somewhere at this particular point we get altogether austenite composition throughout with 0.4% of carbon dissolved interstitially in the austenite grain boundary, and it will not have any difference until it reaches this line, which is A3 line. So it will have the same 0.4% of carbon in the interstitial portion of the iron lattice up to the upper critical temperature line on the hypoeutectoid side of the steel. Upon reaching this line, just below that, this is where the allotropic change has to start. Like we have already seen in pure iron, the allotropic change starts from 910. Since carbon is being added, there is a difference in the temperature at which it is supposed to occur. Instead of 910, it is occurring somewhere here below. And at this temperature, the starting or the beginning of transformation is to initiate, and it will transform from FCC gamma iron to BCC alpha iron, and the allotropic change is beginning at this particular point. So all the allotropic changes is initiated just below this upper critical temperature line on the hypoeutectoid side of the steel. Now, in order to change from FCC gamma iron austenite, the carbon which is present in the interstitial solid solution has to come first out, and they have to just dissolve only 0.025% of carbon and form a alpha iron like shown in this case, and the rest of the carbon which has come out from the gamma iron will be absorbed by the other gamma iron or austenite, and that is how the austenite will increase its carbon content and will try to attain the eutectoid composition, which is 0.8, and it only dissolves 0.025% of carbon in order to form alpha iron. And this alpha iron which is formed will grow in size from this point until it cools to this point. So as it cools down, the amount of ferrite which is formed will only vary, but at the same time the rest of the austenite will attain more carbon, and it will try to attain the 0.8% of carbon, which is exactly required for the eutectoid reaction to participate. So below this line, or the eutectoid temperature line or lower critical temperature line, all the austenite will attain 0.8% of carbon, which is exactly required for the eutectoid reaction to occur, and the austenite will now transform into the eutectoid reaction, which is nothing but ferrite plus cementite mixture, which is perlite. So it looks something like this. We'll come to this perlite formations, but mainly you'll have the austenite which is transforming into alternate layers of ferrite plus cementite, like shown in this case with the hashes, and the alpha which is ferrite which is formed even before the eutectoid reaction was called as pro-eutectoid ferrite. So in 0.4% of carbon we get pro-eutectoid ferrite and perlite mixture. Now when we discuss about 0.8% of carbon, at this particular point it will have more or less the same austenite, only difference will be its carbon content. In this alloy, we have 0.8% of carbon dissolved interstitially in the austenite grain boundary, and at this particular point it behaves like a pure metal and completely transformed. 100% of austenite will be transformed into 100% of perlite. So it will all transform into alternate layers of ferrite and cementite network, like a laminar or a fingerprint like structure, as you can see here in this case. So main process behind this transformation of austenite to perlite is through diffusion. So the carbon which is coming out from the austenite will form first initially a plate-like structure, which is a rich in carbon. So it will form a cementite Fe3C. So this carbide on either side of this carbide will form a ferrite with only 0.025 percentage of carbon, and that forms an alternate layers of ferrite cementite network, which is looks like a laminar structure. So further, if we focus on something in hypo hypereutectroid side of the steel at let us say 0.1 percentage of carbon, at the austenite grain boundary you'll have the same austenite, but in this case 1 percentage of carbon dissolved in the austenite grain boundary, and it will not change until it reaches the upper critical temperature line, which is ACM. Here already we have reached the eutectoid composition that is required to form the eutectoid reaction, and it is excess now, and whatever is excess, this line will represent a saturation limit. That is, above the line you have unsaturated carbon dissolved in austenite. At this line you have saturation, and below this line you have the precipitate of saturated carbon. So this line basically represents the saturation limit of carbon in austenite grain boundary. So below this line, the carbon which is rich will come out as a cementite network around the austenite. So whatever is the excess carbon that is dissolved, as it cools below this upper critical temperature line on the hypereutectoid side of the steel, will transform as the carbon which is coming out and form a network around the austenite grain boundary, which is something like this, and it will continue to grow until it reaches this low critical temperature line, or it is the eutectoid temperature line, and the austenite try to maintain only that percentage of carbon which is required for the eutectoid reaction, which is 0.8 percentage of carbon, and rest of the carbon will be forming in the form of cementite network around the austenite grain boundary, and this austenite which is present will transform into again the perlite reaction, because already 0.8 percentage of carbon is only being maintained and remaining carbon is being formed in the form of cementite network. So it transforms into protectoid cementite plus perlite. So here, as to summarize, we get a protectoid ferrite and perlite at the room temperatures when we have a carbon composition less than 0.8, which is a hypoeutectoid composition, and exactly at 0.8 we get only perlite, and when you have hyper eutectoid steel, then we get protectoid cementite plus perlite. And the important thing to remember here is this A3 line represents an allotropic change, and above this there is gamma iron, which is austenite, and below this you have both gamma and ferrite. So this line represents the allotropic change, which is upper critical temperature line on the hypoelectric side of the steel, whereas this line ACM represents the saturation limit of carbon in austenite. So this line above which there is unsaturated carbon, and as it cools at this line it becomes saturated, and below that any supersaturated will come out as a precipitate and it forms protectoid cementite. So this is how you are supposed to remember, represent, and try to get good marks in scoring the iron carbide diagram with the concepts and the diagrammatic representation. I hope I am was fair enough in discussing most of the important concepts. Thank you. This is how you can contact me, and further looking forward for some more such videos.